Welcome to our channel. Today, we're diving into one of the most fascinating concepts in physics, the twin paradox. This thought experiment has puzzled scientists and science enthusiasts for over a century, and for good reason. Get ready to explore how this mind-bending idea challenges our understanding of time and space. We'll break down the science behind it, examine its implications, and delve into whether it could ever become a reality. Imagine identical twins, Astra and Nova. Astra embarks on a high-speed journey into space aboard a rocket ship traveling at a significant fraction of the speed of light. Nova stays on Earth. According to Einstein's theory of special relativity, time is relative to the observer's frame of reference. This means time can pass at different rates for observers moving relative to each other. As Astra zooms through space, time for her slows down relative to Nova. This phenomenon, known as time dilation, is due to the constant speed of light in a vacuum. To Astra, time inside the spaceship feels normal. However, from Nova's perspective, time on Astra's spaceship appears to move slower. After years, Astra returns to Earth. She finds that more time has passed on Earth than for her during her journey. Nova has aged significantly more than Astra. The paradox arises from the seemingly symmetrical nature of the situation. The resolution lies in understanding the asymmetry of the twins' journeys, which we'll explore next. To grasp why Astra ages less than Nova, we need to delve into Einstein's theory of special relativity. This theory, proposed by Albert Einstein in 1905, revolutionized our understanding of space, time, and motion. One fundamental postulate is that the speed of light in a vacuum is constant for all observers, regardless of their motion relative to the light source. Imagine you're standing still and shine a flashlight. The light travels at the speed of light. Now, imagine you're on a moving train and shine the flashlight again. The light still travels at the speed of light, even though you're moving. This constancy of the speed of light is counterintuitive, but crucial. This might seem like a contradiction, but it's a fundamental aspect of our universe. It challenges our everyday experiences and requires a shift in our perception of time and space. To reconcile this, Einstein realized that time itself had to give. Time and space are interwoven, and changes in one affect the other. As an object approaches the speed of light, time slows down for that object relative to a stationary observer. This phenomenon is known as time dilation. This time dilation is a real physical phenomenon. It's not just a theoretical concept, but has practical implications and has been observed in various experiments. In the twin paradox, Astra's high-speed journey causes her to experience time dilation relative to Nova. This means that while Astra is traveling at high speeds, her clock ticks slower compared to Nova's. From Nova's perspective, Astra's time slows down, resulting in Astra aging less. When Astra returns, she is younger than Nova, who stayed on Earth. The resolution lies in the fact that Astra and Nova don't share the same inertial frame of reference. Their experiences of time are fundamentally different due to their relative motions. Astra undergoes acceleration at various points during her journey. These accelerations are key to understanding the asymmetry in their aging. These periods of acceleration break the symmetry of the situation. They create a distinction between Astra's and Nova's experiences of time. Unlike Astra, Nova remains in a relatively inertial frame of reference on Earth. Her experience of time is more uniform and less affected by relativistic effects. Time dilation has been experimentally verified using atomic clocks flown on airplanes and satellites. These experiments confirm that time indeed slows down for objects in motion, validating Einstein's groundbreaking theory. Could we observe the twin paradox on Earth with our current technology? The answer is complex. While we have evidence of time dilation on a smaller scale, replicating the twin paradox scenario presents challenges. One primary obstacle is the speed required to observe noticeable time dilation. Our fastest spacecraft only reach a tiny fraction of the speed of light. At these speeds, the time dilation effect is measurable but too small to be perceived by humans. To achieve significant time differences, we would need propulsion systems capable of near-light speeds. This remains in the realm of science fiction. However, we can explore time dilation using ultra-precise atomic clocks at different altitudes. Experiments like this have confirmed Einstein's theories. Particle accelerators, like the Large Hadron Collider, also allow us to observe time dilation effects directly. Certain particles' lifespans increase significantly when accelerated to near light speeds. The twin paradox arises from the seemingly symmetrical nature of the twins' journeys, which at first glance appear identical. From Astra's perspective, it seems valid to claim that Nova is the one moving away at high speed, creating an illusion of symmetry. This apparent contradiction is where acceleration becomes crucial, as it introduces a key difference in their experiences. Astra's journey involves periods of acceleration and deceleration, which are pivotal in breaking the symmetry. These changes in velocity break the symmetry of the situation, making Astra's experience fundamentally different from Nova's. During acceleration, Astra is no longer in an inertial frame of reference, which is a key factor in the paradox. Nova, on the other hand, remains in a relatively inertial frame of reference on Earth, experiencing no such acceleration. This difference in frames of reference is key to understanding why Astra ages less compared to Nova. Einstein's theory of general relativity, which deals with gravity and acceleration, helps explain this phenomenon in detail. According to general relativity, acceleration and gravity are equivalent, a principle known as the equivalence principle. Being in an accelerating frame of reference is indistinguishable from being in a gravitational field, affecting the passage of time. Astra's periods of acceleration can be considered equivalent to experiencing a gravitational field, altering her perception of time. This affects the flow of time around her, causing her time to slow down relative to Nova's, who remains on Earth. The resolution of the twin paradox lies in recognizing that the twins' journeys are not symmetrical due to acceleration. Astra's acceleration breaks the symmetry, making her the twin who experiences less time overall, as predicted by relativity. It's not just about who is moving, it's about who is accelerating, which is the crucial factor in the paradox. This understanding resolves the paradox, providing a clear explanation based on the principles of relativity. The concept of time dilation is not just a theoretical construct. It has been experimentally verified numerous times. One compelling piece of evidence comes from experiments involving atomic clocks. Atomic clocks are incredibly precise timekeeping devices. In the 1970s, the Hypothetical experiment used cesium atomic clocks to test time dilation. 4 atomic clocks were synchronized and flown around the world on commercial airplanes. Upon their return, the clocks were compared to a reference clock. The results were astonishing. The clocks that had flown eastward lost a tiny fraction of a second. The clocks that had flown westward gained a tiny fraction of a second. These differences were in line with the predictions of relativity. This experiment provided compelling evidence for the reality of time dilation. Beyond atomic clocks, time dilation effects are also observed in subatomic particles. In particle accelerators, particles are accelerated to near light speeds. Certain particles, like muons, have a very short lifespan. When accelerated to near light speeds, their lifespans increase significantly. This increase is a direct consequence of time dilation. Let's venture into the realm of hypothetical transportation on Earth, where the boundaries of our current technology are pushed to their limits. Imagine a train capable of traveling at a significant fraction of the speed of light, zipping across continents in the blink of an eye. While such a feat is currently beyond our reach, it presents a fascinating thought experiment that challenges our understanding of physics and engineering. Imagine boarding this futuristic train in New York City, eager to reach Los Angeles in record time, cutting down a journey that usually takes hours to mere minutes. As the train accelerates to near light speed, the scenery outside would warp and distort, creating a surreal visual experience. Inside the train, everything would feel normal, with passengers enjoying a smooth and comfortable ride. Time would flow as usual, and the laws of physics would remain consistent for those on board, allowing for normal activities and interactions. For those observing the train from a stationary point, time dilation would be evident, a phenomenon predicted by Einstein's theory of relativity. The train would appear to contract in length, and time aboard would appear to slow down, creating a striking contrast between the experiences of passengers and observers. This difference in the passage of time would become pronounced as the train approached the speed of light, highlighting the bizarre effects of high-speed travel. The implications of such a high-speed transportation system would be profound, revolutionizing the way we think about travel and connectivity. Travel times would be drastically reduced, making long-distance travel almost instantaneous and reshaping our global landscape. However, the technological challenges are immense, requiring breakthroughs in materials science, energy production, and safety protocols. The energy required to accelerate a train to near-light speeds is astronomical, posing significant hurdles for practical implementation. While a near-light speed train remains science fiction, it prompts us to ponder the limits of technology and the incredible possibilities that lie ahead. Thanks for watching. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more fascinating science content. The twin paradox continues to captivate our imaginations and push the boundaries of our understanding of the universe. Leave a comment below with your thoughts on the twin paradox and any other topics you'd like us to cover.